of the 2 weeks. You've seen experts talk about their fundamental techniques and principles, and now it's up to us, the food scientists, to fill in the holes, plug the holes, and actually show you how you use all these fundamental principles in the study of a food material. So today I'm going to talk to you about science, a little bit of philosophy, and a little bit of art, and a lot of history. So this is a historical piece for you. And I'm going to talk to you about fat. And anytime I do work these days, and I challenge you to do it the same, to actually look at motivation and a problem. And it's not like problem like your friendly neighborhood physicist would call a problem. It's like, are you trying to discover the nucleus of the atom? No, it's problems that touch us every day, that are part of what we need to do in order to make it a better world. So even though we study physics or food science, that doesn't mean we cannot go out there and burn some rubber tires and try to change the world. So in my area of foods, we're trying to eliminate hydrogenated fats. Remember, heart attacks, hydrogenated fats, those kind of things. Your reduction in the amount of saturated fats, Europe is very active in that respect. Lowering serum cholesterol levels and decrease of cardiovascular heart disease. Greater sustainability. We're blowing it, right? So if we don't change our ways, we're going to lose the world. So less energy consumption, less transportation, less CO2 emissions, less water consumption, less habitat destruction. We don't have as many fish as we should have out there in the Mediterranean, right? The Amazon is suffering, etc., etc., etc. Clean label. We all like to have simple ingredients in the food we eat. And maybe no animal products if you're in the vegan lifestyle, and maybe non-GMO if you don't want genetically modified organisms for some bizarre reason, not welcome around here. So when you're working at midnight and you're thinking what the hell you're doing here and you should be somewhere else doing things, remember, you're part of the solution to the problem, and hopefully you can focus that way as well. Today, I'm going to try to tell you what is this and what is different from this. That's like a margarine or a butter, and the other one is olive oil. So I like to visualize what I study, very visual person, right? So if you ask a physicist or somebody to draw their system, you should be able to draw it very simple. I'm going to tell you what milk is. That's milk. Okay, so that's the beginning and the end all. You have to have a mental picture of it. So when I came into the field, so what is a fat? That thing you put on the bread and you spread it. So to the chemist and the chemical engineer, and here I go insulting every discipline, of course. It's a complex mixture of high melting point triacylglycerols, which are the molecules that make up all the fats. I'll show you the structure in a second. In a low melting point triacylglycerols with complex phase behavior. And all can be explained, we try to explain things as scientists, right? From knowledge of the molecular composition and from phase behavior. So the amount of solid crystals present and the phase diagrams are the king. This is the realm of the chemical engineer. So if you're a crystallographer and you bought yourself a nice X-ray diffraction unit and you're going nuts and you like to go to the synchrotron, you go, no. That's not what a fat is. A fat is a metastable polycrystalline material prone to recrystallization and fractionation. All can be explained from knowledge of the solid state and polymorphism. So the X-ray diffraction unit is the king, and the differential scanning calorimeter, which measures melting points, is the queen. Now, but if you're a colloidal scientist, I see a lot of you guilty people here. If you're a colloidal scientist, you say, no. A fat is a colloidal gel or a colloidal crystal composed of a network of polycrystalline fat particles which trap liquid oil within. All can be explained from knowledge of the mesoscale structure. You have a lot of really nice microscopy. So colloidal sizes, interactions, distributions. So the rheometer is the king, but the microscope is the queen. Now, to the consumer, it's something that makes you fat, but it tastes good, and the cookies and the chocolates rule. That's a dichotomy of food science, right? And I'll try to make an argument to you today that fat is a network of triacylglycerol primary crystals and polycrystalline crystals clusters with different amounts of liquid oil trapped within. So next time you go out there and spread that butter on that bread, you'll have new respect for the stuff. So this was a potpourri of the early days when I came into the field. I'm a biophysicist, if you may. I study biological membranes, spin labels, phase transitions, that kind of thing. And I ended up in food science. Can happen to you too. And so I arrived there and I say, so what are people doing in this area, right? And you're like, oh my God, what's happening here? So there were molecules, there were crystals, there were cone penetrometers. And there were solid fat content measuring machines developed by Unilever and a little bit of microstructure. And I'm going to tell you a bit of the story, but at the same time, just a little potpourri. So don't expect any logic in what I'm about to show you. So let's start with the molecules. This is what I was faced with. Okay, this is a triacylglycerol. All the fats are made of this. All of them. The 95% of the stuff is this. You have a glycerol backbone and 3 very long chain fatty acids usually 18, 16 carbons long. They can have different amounts of structures, but so ester bonds, so here are the ester bonds attached to an acid, triacylglycerols, and a glycerol backbone. So you need to understand this molecule a little bit to understand the behavior. Now, the problem is that it's not only that we study a single molecule, they're mixed systems. Now imagine if each one of those chains could be 14, 16, 18 carbons long, or 8 or 10 and 12, or all of them all together, or 4 or 6. Butter has a ton of 4, all the way from 4 to 18. Imagine that complication there. Then they can have double bonds, 2 double bonds, 3 double bonds, fish oils, omega-3 fatty acids, omega-9 fatty acids, which are nomenclature which you probably don't know, but it's just where the double bond is. And they can be simple homogeneous, which never happens, of course, or they can be mixed heterogeneous. So you have a massive multi-component system. You're not dealing with a single molecule, you're dealing with a mixed, gigantic, complex system. What else was known at that area? So that was known very well. So there was the work of Jensen and Mavis, 1963, the single crystal study of the tricapran, C10, pure. And they had very nice single crystal study, so we understand how this thing fits in a crystal. We know about the unit cell, we know about angles, crystallographic angles, we knew that. And there was maybe one on trilaurin. That's still open to debate whether Larsen had the trilaurin structure or not. He published it in some obscure Danish journal. Don't do that. In another language. So whatever. And there was also the work since 1939 of Malkin, 34, I'm so sorry, in which he tries to analyze the polymorphism of this without indexing planes. So it's just like, oh, I see reflections here and here and here. I see reflections at 3.7, 3.9, 4.6, and that is a beta form, or for even an odd acids, or an alpha form, or a glass. And then they spend the next 20 years screaming at each other whether a glass exists in fats or not. There's no fat glasses, by the way. They're all crystals, irrespective of how quickly you cool them. And then, of course, there's a lot of famous people that came after it, simplified things afterwards. And also, then, people would put a photograph like this in front of you and go, look at my crystals. I'm like, wow, with a polarized light microscope. And look, this is 200 micron scale bar. So I'm like, wow, those crystals are really big, eh? And okay, whatever, I know nothing about this area, so it's whole thing is a little confusing. And then you go to the lab, and I inherited a lab with John DeMann, a venerable fat scientist, and then he had things like this, the cone penetrometer. You grab this thing, you put it on top of your fat, you have cones of different angles, like throwing a lance to your food system, and then it goes in, and and then you read the dial, how many tenth of millimeters it went into the fat. It's very nice. And depending on how deep it goes, he had a little formula in which you calculate the yield stress. Now, pretty good, eh? You saw very complicated things. Look at that. And so even with it's an empirical relationship he established there. But then that didn't end there. He did measurement of margarines and shortenings by means of great number of thumb tests compared with yield values. And the thumb test is still used today. It's very difficult, and if you need help, you can come train with me. It's like this. You actually thumb into the shortening, and the expert, fat maker, knows exactly what that thumb should feel like. And so he put here a yield value and things like very soft to just pourable to too hard. Isn't that cool? And then at the end, he related this yield stress to different applications. Puff pastry margarines, cake margarines, shortenings margarines. So that was like, wow, this is really advanced in this area. That was 1959 and still used today. And then you have the crazy people at Unilever who develop a pulse NMR, because fundamentally, as I will show you, many of the properties of this material depends on the amount of crystalline material that is present. You know how difficult it is to determine how many crystals there are in a piece of butter? Like, it's not easy. You can do it by density differences. It's a nightmare. So these guys developed a little, this is a 20 megahertz NMR, pulse NMR. So with a pulse NMR, you can actually determine in about 4 or 5 seconds the amount of crystalline protons or less mobile protons versus faster protons. You may have seen something like that. You have a free induction decay of a nucleus, you know, after an RF pulse. Then there's a dead time of the receiver, and then you see a voltage dropping, and these are the protons demagnetizing. And so in here you have both the solid and the liquid protons. You take a signal about 11 microseconds, then you take another signal at 70 microseconds, and you do a ratio of the two. So basically, solid plus liquid minus liquid is solid. That's it, divided by the total is percentage. Times an F factor, which is the very venerable in our area called fudge factor. And the fudge factor is because you have a dead time of the receiver here, and you cannot measure that point. It can be as high as 25% that you multiply it up. And then you determine the SFC, because the SFC is one of those indicators of functionality, macroscopic functionality of your material. If you work in the fats and oils area, people are going to try to sell you fat based on SFC. So it's like money. They tell you like SFC at 10, 20, 30 degrees, and you go, and you give them money, and you get the fat. Now, so here's an example of what we can do. We were interested in matching animal fat with vegetable fat, so we developed a glycerolysis method, which I'm not going to cover. You can read it in the Nature Food article. And we can sort of match things like beef fat. And then this is an enzymatically transformed fat without adding anything to it, just rearranging those molecules in there. That's pretty close. And here I think we matched the palm olein GP with pork fat. So we were matching, and so this is what I mean by functionality. Everybody's trying to look for indicators of functionality, so that's not too bad. If you measure the SFC at different temperatures, you go, these fats must be the same, right? Because they have the same amount of solids at different temperatures. Yeah? Well, the thing about this is that you don't take into consideration structure whatsoever, right? It's just solids. Solids are solids are solids. I mean, who cares if they're big solids or small solids? And then again, the Europeans are guilty for this. There was these fringe people like Van den Tempel who actually try to think about the fat as a colloidal system. So to him, fat was this. Look at his drawing. That's fat. There. So he said it's made of particles, and the particles are interacting via van der Waals interactions, and we just have chain of little particles. Come up with an expression like that. He took the geometric average of the expression for van der Waals for cubes and spheres. That's how he got the 3.5. I do not know if that's correct. I'm actually sure it's not correct. But anyways, so this is just a van der Waals between spheres. You put it into some rheological linear model, and you get this. It didn't work, but it was the first time somebody thought about that. Then that was in 63, and then you see academics, we have the pleasure of going back in 79. How many years is that? That's like 16 years later going, damn it, it didn't work. So he says, we have to consider clusters of particles, not only single particles. And if you read that, so he said maybe it's not a linear function, it's some sort of power law function of the elastic modulus. And then, he's talking about scaling factors. He didn't know what he was talking about, but he realized that it was actually necessary. And then came this guy here, Ron Vrecker. I met him in Unilever, and he said, well, maybe they're fractals. It's like, ooh. And he dispersed some fat crystals in mineral oil and took some light scattering. He saw the power law of the intensity versus Q, and everybody was, yay. He was given wedgies. You know what a wedgie is? It's when they pull your underwear up underneath your pants. So in Unilever, he did not garner respect from the Unilever University because they were tough guys. If you went to the Unilever Research Center with 1,500 like people with big heads, it was a scary place. You were like on guard all day, and they thought he was insane for saying that a piece of butter is a fractal. But he proposed it, he put it out, he used a strong linked regime, meaning the particles yield and the bonds are stronger than the particles. He'll say more about that, and it was the first time that he did that. And then his colleague, that they don't ever talk to each other, Isaac Hertzje, he was amazing. He was doing scanning electron microscopy and measuring, look at that. He was trying to image the fat, maybe trying to look for those clusters, the blobs that are made up of particles that somebody talked about, the clusters that Van der Tempel said. Just very confusing. And he also started talking like this. Maybe if we mix fat and emulsifiers, aqueous, and we put some external fields, we get a microstructure. Wow, a microstructure. What the hell is a microstructure? And maybe it's related to the microstructure that we get properties like binding of water, stability, salt release, indicators of macroscopic functionality. That's where we came in. And we said, okay, this is just bizarre. And we started putting things like this up in the 90s. In about the mid-90s, we started putting this. And I said, well, and of course we did some experiments, just a few experiments, and they put out the diagram. It's like cartoons go a long way in science. You put one of these things up, it lasts forever. You don't have to have much data behind it. So triacylglycerol molecules at the bottom of it eventually become supersaturated from the melt. They form crystals. Nobody knew what a crystal was. Everybody showed me those gigantic balls under the polarized light microscope. That's not totally true, but more or less. Then these crystals form clusters. Oh, that didn't exist. Sort of didn't exist. We always build upon somebody else. I mean, they probably saw it, but didn't know what they were looking at. Crystals, then that forms a network, and then the network gives you the fat. And you have here the rheology, the mechanical strength, the sensory impressions. If you do rheology and you go wiggy, wiggy, do you really think you're moving molecules around? Not in the case of these hierarchical structures. They're extremely hierarchical. So we have nanoscale, we have mesoscale or microscale, and we have the macroscopic world. You can put your own boundaries to that where you want it to be. And all of these steps are affected deeply by external fields. Heat, mass, and momentum transfer affect each one of these things. What a nightmare, right? So equilibrium thermodynamics, equilibrium consideration of this is almost meaningless. And then every time you get yourself a machine, you need to be cognizant of what the hell you're analyzing. So if you have the solid fat content, you're probably doing what? The crystal network is made of solid crystals, the clusters as well. So it's anything that is crystalline. If you do polymorphism, you're down here at this length scale. Not here, here. So up to you to go from here to here, which is people are trying to always jump, right? Finding which length scale is giving you your properties. And so be it. You buy yourself a gas chromatograph. You buy yourself an infrared spectrometer. You're down here. If you can go from molecules to here, congratulations. You're on the boat to Sweden. So we came out and said, well, maybe then we should be a little more holistic about this. Do you like my choice of colors? That's a phase contrast micrograph of the high melting fraction of milk fat in an ocean of liquid oil. And of course, it's birefringent. Fats are birefringent, things like starches. And look at those fractally looking things, eh? I mean, just the feeling was there. And I chose pink, by the way. So the factors that affect the functionality of your material are the solid fat content, more solids, harder, not that hard. Primary crystal habit, so different crystal forms, polymorphism, different melting points, right? So that's going to affect. Anytime you eat chocolate, think about polymorphism, as you will see. But what about the nano and the microstructure? Can we address that, please? Pretty please. So crystal morphology and size, maybe spatial distribution of mass, fractal dimension. And what about interparticle interactions? Is it all van der Waals? Can we put electrostatics in there? What can we do? So I'm not saying that I have the solution to this. It's saying, what about making a list? I like to make a picture and making a list. Okay, so that at least you know where you are. What's your phase space if you're moving? So let's start from the very, very beginning. Now you know what a triglyceride is, so let's crystallize it. The melt, depending where you are, and I'll show you some really nice neutron scattering studies, it's isotropic. So these are the molecules that were nicely, if you remember that crystal, you know, with the chair conformation or the tuning fork. They have nice names. Tuning fork, beep, for tuning your guitar, and a chair, like a chair with a seat, two legs, and a backing. But here, they look like spiders. So you have spiders in the melt. Next time you melt butter, think of spiders. And you decrease the temperature below the melting point of the solid, you enter something that is called the metastable region. It's almost like you have a sugar solution and you drop the temperature. Let's say it's 40 degrees. You drop, it's like, uh-oh, I have to crystallize because I am supersaturated. Same thing in the melt. So you got supersaturated, and then you form a crystal. And look how the crystalline solid is. Fairly easy. You have a long axis of the unit cell. These things are gigantic. We're talking like 40 angstroms. And these guys are like 3 to 4 angstroms. So you can really detect it in an X-ray diffraction pattern because you have this monster peak at very low Qs. And that is how big these lamella are. They stack in these sandwiches and sandwiches and sandwiches, and I'll show you what happens in a second. So crystallization in any material, you see you're here below the melting point of the material, which is an oxymoron, because like what's the melting point of butter? Let me tell you, it starts melting at -30 and it ends up at like +40. What's the melting point? It's a problem when you do with complex systems. So it is maybe the highest melting component. Let me complicate it for you more. Depending on the phase behavior, maybe it's a complex of 2 or 3 molecules that are coming down. God knows. I mean, there's a lot of them, right? So melting point is a loaded thing. When people tell me the melting point of butter, I laugh a little bit, but it's okay. Nucleation and growth. 2 things that happen during we haven't talked about crystallization, so let's do that. But before that, wouldn't it be very nice? We have a multi-component system, many different molecules, blah, 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 so very complicated. You have to be a patient person. And but it's highly polymorphic. So polymorphism is you have the same chemical composition, whatever that means, because remember, this is a mixed system, right? And you can have different solid-state structures, from the most metastable to the most thermodynamically stable. This is a hexagonal packer, this is orthorhombic perpendicular, and this is a triclinic. I mean, that helps you if you do more advanced crystallography, but the important thing, lower melting point, lower density, lower stability, higher melting point, higher density, higher stability. And it's monotropic, the phase transitions that go from one to the other one, meaning always from the least stable to the most stable. No, it's not going to go backwards. You know, it only goes that way. And very important, these polymorphic transformations in fat. If you go to the fat maker, they go margarine. Oh my God, margarine, beta prime. You go to the plant that makes the fat, and they talk about beta primes. It's amazing because beta primes are associated with small crystals that give you a finer structure and greater plasticity. Bigger crystals give you something like chocolate, as we will see in a second. How do we understand this weird polymorphism? Is you have 2 things. I told you that the beta was more thermodynamically stable than the beta prime than the alpha. Hexagonal, orthorhombic, triclinic. And obviously in a free energy diagram like this, the beta would be at the lower energy level. But we must not forget the energy of activation. So the energy of activation of the beta form, even though you would say, oh, my driving force is thermodynamic, I'm going to go to the beta form, because the energy of activation of the beta form is the highest. Beta prime is the least, and alpha is the lowest. So irrespective of what you do, you cool this thing down, the viscosity goes through the roof, the diffusion is like arrested, and the thing goes, I got to get out of here. I got too much supersaturation. I need to crystallize. Let's go to the alpha. It does it like that, always. Unless you go super slowly, right? And who does that anyways? Alpha, and then very slowly the fat goes, oh, I think I'm going to go to beta prime, and depending on the molecular structure, maybe I'm even going to go to beta. And then you get defects in chocolate, my form changed, now it doesn't melt in my mouth, it's waxy, or you get big crystals that have recrystallized into the beta form. It's a catastrophe. A margarine maker's nightmare is to go from the beta prime to the beta. So a lot of people that crystallize fats is a story of controlling polymorphism, particularly chocolate. Chocolate is like super critical. And so how do we understand this solid state structure? And I apologize to anybody who does crystallography. It's like, here's the unit cell of a crystal. Here's notice how it looks like a chair? This is the back of the chair, and here are the legs, right? Or if you want to call it a tuning fork, it's slightly different. Here's the glycerol core. So here you see the C-axis of the unit cell, the long one. You can't miss it. And then you have 2 of the shorter ones. This is, of course, the plane, the CA plane. And so we're talking about this whole thing. In fats and oils, they don't characterize, because it's so long ago, they based it on the long-chain alkanes. So they did a 2-dimensional representation of the unit cell, and they call it the subcell. So all they're looking at is the reflections associated with the long alkane chains, which are very similar to to long-chain alkane chains, not the fatty acid per se. So nobody does indexing, believe it or not, in this area. And you just look at the relative packing of the ethylene groups. And that is what defines alpha, beta, prime, beta. You put in the X-ray diffraction unit, you get the peaks where you are, and you go the number. Most people don't know what the number means, but it is the packing of these long chains. So these long chains are defining the polymorphism. The packing of the long chains define the polymorphism. But let's not forget that we also have the long axis of the unit cell, this guy here. And you can see, yeah. Absolutely not. Absolutely not. That surface is cool because I like to call it epitaxial growth, even though some crystallographer is going to shoot me if I do that, but I like it. So, I mean, it's almost like epitaxial growth of these lamella. Super important. What's the structure of this? How irregular it is? We've done some simulations. It's pretty crazy. Imagine if you have a mismatch of chains and you have these things popping out, like extra 2 carbons for fun. I mean, how do these things like stack relative to each other, and what are the effects on functionality? Can you destabilize the system and lower the melting point? Ooh, interesting. What is the nature of a eutectic between 2 things that are really rough and don't fit very well one next to each other? Ooh. Anyways, this is a long axis of the unit cell. You can have 2 carbons because it's about, you see, if you pack it like this, 1, 2. And so if you know how long the carbon chain, you multiply it by 2, and if you get a reflection around that, that's what you got. Or it can be 3. Now, the other one is about 42. This one's like 64. Like, okay, you know more or less that you have a 3L packing. Notice how you have in the center of the triglyceride something odd. Then it hangs out together, and then you have 1, 2, 3 fatty acid chain lengths per that. So as long as you can multiply 2.5 by any number between 1 and 20, you got it. Beautiful question. They can do whatever they want. You can have a 3L alpha. Chocolate, you have the 3L betas that give you the nice melty characteristics. The 2L melts in your hands and not in your mouth. I mean, melts in your hands and not in your mouth. So the 2L for chocolate is bad. It needs to be 3L, but it needs to be beta. On the way to like crystallizing in the metastable region, milk fat, because it's so heterogeneous, the baby cow gets all the benefits of that heterogeneity. They form 3L alphas, which then change to 2Ls. And then it stops at 2L because it's too random, the distribution. It cannot go to beta. It just can't get to the most stable, thermodynamically stable. It just cannot do it. It's just too heterogeneous. So there's a whole zoo of that depending on the fat. And so this is a bit of a lecture, right? So somebody like gives you this, and the fat maker goes, okay, at least hopefully you remember alpha, beta, prime, beta at the end of all of this. So look at the hexagonal packing. The hexagonal is characterized by 1 characteristic reflection, as you will see in a second. And you get 1 massive peak at 4.1 angstroms. Show you where that comes from. The beta prime is characterized by 2 characteristic lengths. But you look at that, you say, oh, they don't do indexing. You know how impossible it is to do indexing with this garbage? Impossible. Absolutely impossible. What, you have 4 peaks and they're like all deformed because you have a multiple component system. So, bootstrapping, gentlemen and ladies. Meaning, you do the best you can. So 4.1, 3.8, 4.2, and here characteristic reflections for the beta form, 3.7, 3.9, and 4.6. And look at these nice ones. These are the lamella I talked to you about. And so the lamella here are like 47 angstroms, and these are lamellar faces. And if you get peaks from a lamellar face, they space as 1, 1/2, 1/3, 1/4. They're like that, integers. So 45 divided by 3, 15. So this is the 001 reflection. This is the 003 reflection. And you can get many more, as I'll show you for chocolate. But look at this cool thing. Remember how the alpha is like metastable and trying its best to crystallize, but it's a catastrophe? Look how much bigger it is, 47.3. It's hexagonal, so it's standing like this, the chains, and they're like big. And then when it goes to beta prime, it goes, oopa. And it goes a little bit like this, and it becomes like 45. And then it goes a little more oopa maybe, or whatever it decides to do, does whatever it wants. And it goes to the beta form that is more, so you see it goes from 47 to 45, maybe, and then it stops. It seems like that was enough to get to the most stable form. You were wondering what those peaks were? Well, Sato showed and Abrahamson showed in 1978 that if you have, you know what this is? This is really weird. If you had a triglyceride, I told you that's that spider with the 3 long legs, and I turned them to you. That's what you're looking at. And this round thing means that they can have any orientation. You know how many years it took me to realize that? I mean, they show me these balls. Structure like that. It's like, what? That's a triglyceride. It's like, are you nuts? I mean, it's like, okay, so this is the subcell, on the on view of the thing. So they can be oriented in any way. Hexagonal packing, grab a bunch of pencils and look at it. It's all hexagonal. And so it's the easiest kind of packing you can achieve. There's one characteristic length, 4.1. So peak at 4.1, right? Yes, sir. Yeah. Yes, they do. They rotate in the crystal. That is a question that everybody's trying to still discuss, whether we have melt-mediated or solid-state transfer. That's a very important question. In chocolate, there's the debate that when you actually get to even the more, there's groups that think that even here you can have movement in the solid state. But nobody has done that NMR experiment. No, I would say that it's not clear out there. Sato from Japan, he's convinced that there's a solid state. He has a lot of data from IR. He does IR. But that's an excellent question. That's a more advanced thing, is whether you can actually have this important polymorphic transformation. You need to melt it before and recrystallize. That's a different story than if you had actually a solid state and it goes like that. And then orthorhombic, 2 characteristic distances, 4.2 and 3.8 angstroms. Angstroms, not nanometers. 0.3. We had this discussion. Sorry, it's a nanometer. Because Sato in Japan doesn't have the angstrom sign. I don't know what's wrong with their alphabet. They don't have in Word the angstrom, so he uses nanometer for everything. I like angstrom. It's sort of historical. I like history. And then the beta form, the triclinic form, has 3 characteristic distances, which correspond to the 3 peaks I showed you. So that's where that comes from. And then you would see in textbooks things like this: alpha, beta prime, beta. I'm giving you the full-on way the things are. Nobody talks about this. They give you the reflections. They know that. And the density is obvious. The melting point is obvious, right? What else is obvious? Texture. This is not obvious. Smooth and grainy. Now we're beginning to get like interesting here. And in the microstructure, platelets, tiny needles, long needles. So it came to the point where people were looking under the microscope and going, that's a beta form. I'm like, no, it's not. Like, how do you know it's a beta form? Oh, because it looks like long needles. And these are the sizes associated with those structures. This is in textbooks. This is in food science textbooks. So if you're a fat maker, you like the beta prime because they give you small needles with a smooth texture in your margarine or your butter. Now, isn't that relative to the times? Lots of love. Chocolate. So this is the first test. We're going to go through what you just learned, and we're going to make chocolate. So here's a triisoglycerol molecule. Believe it or not, the R1, R2, R3 are the 3 fatty acids. Cocoa butter is very homogeneous. It has really 3 fatty acids, 16 carbons long with no double bond, 18 carbons long with no double bond, and 18-1 double bond in the middle at carbon number 9. And what cocoa butter likes to do is to put that, when it crystallizes, puts the weirdo 18-1 with the double bond in the middle. And that's why you have this discrepancy in the packing. It puts the 18-1 next to the 18-1 so it can pack it better in the solid state, and puts the saturated ones on the side. So ultimately, it wants to reach here. Even though after so many years, people still do not pay enough attention to the fact that properly tempered chocolate needs to look like this and not this. Because remember, polymorphism was the packing of the long fatty acid chains, not of this thing. So there's diagrams like that from Beckett. And so you have, these are all the polymorphs that you can get in chocolate. What a nightmare. So next time you see the guy with the long white hat going like this on the marble table, you know what he's trying to do? He is undercooling the melt. He is inducing nucleation. And he is grabbing that and putting it back in his bucket, which is still warm, melting the metastable forms just right. You want to get to form 5. So he melts it, but he doesn't go above 32, right? So he melts the metastable ones he nucleated. He melts them, leaves behind the ones that are good, survive. He repeats it 3 times until he has about 4% of this guy. Then he goes into your tablet, into the cooling chamber, and there you go. Now, maybe after next party you guys have there, have a chocolate making party. So you melt the chocolate and you go, I'm going to give you a chocolate, I'm going to put it in the fridge. You put it in the fridge, it's ready. 5 minutes later, look, it's solid. You put it out, it melts. Oh no, you can do that for hours and hours and hours. It doesn't stay at room temperature like solid because you crystallize one of these guys here. Depending on how hot, here would be ridiculous, right? Any of these would melt right away. You have to wait, you have to nucleate it, and then wait for it to transform to the one that is the higher temperature. So you can go back and forth like a lot, and it's never staying, because you are in the lower melting polymorph. Now, the whole business of chocolate is to make form 5, and not 6. 6 is higher melting point. It's waxy in your mouth. It's not melting, right? And that's not, and also it's quite brittle, the material. At that point, the hardness goes up. The 3-point bending hardness goes through the roof. And the guys down here melt in your mouth, in your hand. You grab it. The best way to do chocolate is not a hot day like today. It's just grab the chocolate and hold it. Your hands are not that temperature. And if it all starts melting, you have form 4. And it's not properly tempered. Who needs a DSC? And so here's for your records. Here are different people who give the melting points of the different forms. The different forms, I told you there were 6. They're here, whatever. And here are the characteristic reflections you see to identify each one in powder XRD. I mean, it's just like the phone book, right? And so here's the nice X-ray diffraction pattern. At this point, you would look at this and go, I understand, I see. Your eyes have been opened. And so here we go, and we see the big peak at 4.6. That's character. You go back to the table and you check. That's a beta form, so it's a triclinic. That's what you want for the form 5. And then these guys, hocus pocus, they're in that table there. If you got a certain pattern of these in very scientific, quantitative way, medium, weak, very strong, weak, and strong. Is there very strong? Yeah, there's very strong as well. So that's totally quantitative. And so you look at this pattern here and you go like, oh, it's very strong. This is very strong. And I would say that this is sort of weak or very weak. It depends. And then, of course, you have here the small angle X-ray scattering. And you see the lamella, 65 angstroms, 3L. I told you, multiply 18 by 1.25 or something like that. And you see look at that. We can see 0, I'll tell you about that. Well, 002, 004, 5, blah, blah, blah. You also see a little 46. You got a little 2L, the bad one, the form 4. Not too much. This is like massive, right? So you got a little bit of contamination of form 4 in there. When it's really not tempered very well, you don't see this guy here, and this one is really big when you got the 2L. And I just wanted to show you this that looks very similar to before. That's a piece of chocolate. That's not even the cocoa butter, the fat phase of chocolate. Chocolate is very high in fat, as you know, and sugar. But look at that. It's actually quite impressive that with the machine we can actually get the polymorphism in the whole system. Think about 70% lint, 70% cocoa solids. That includes cocoa mass, the ground up seeds, plus cocoa butter, and the rest is basically sugar. So 70% lint means more or less 30% sugar. 100% lint is just it's the ground up seeds with extra cocoa butter. They actually add extra fat. The British did that to make solid chocolate. Adam did that a long time ago, about 400 years ago, when they made chocolate. Chocolate used to be drunk by the Mayans and the Aztecs as a drink, like coffee, with boiling water. You would boil water into, throw it from a height, create a foamy mess, and drink it. So only the food for the aristocracy and royalty. But that's a little bit heavy, right? But then the Brits turned it into like a tablet. And of course, what else would the Brits do? Add sugar and also fat. And now we have, thanks to them, chocolate. Thanks, Adam. And we've done, as well as using it just for an indicator, we also have done some contributions. Here's the commercial break. For advertisement. We determined that one of the molecules was controlling the polymorphism of the whole cocoa butter, like POS, which is, you have SOS, POS, POP, palmitic oleic. Oleic always in the middle, either PP, SS, or POS. And we found out that the middle molecule, which is an interesting concept, the one that's intermediate between the other two, controls really the movement of the triclinic polymorphism towards the properly tempered one. Then we also discovered a new polymorph of POS. People thought there were one, there were three, so we cleaned that up. And then last year, is it even published this year, we actually found a new polymorph of tristerin, which is 18-18-18, the most studied molecule. People had missed it, and I should have put here the picture of Said Ghazani. He crystallized the material from solvent and waited 2 years. 2 years so that you get an idea of how long in order to get to the final crystal form. So maybe it's not so fast in the solid state, the transformation, but the melting points were between 30 and 36. The literature was a mess. But if you wait long enough, you get to the polymorph 2 years from the solvent. And we also did phase diagrams of the three molecules, trying to find which are the regions of the correct melting point. And this, I think, would help a little bit the mindset to study that. We have also looked at other things that affect crystallization. In this NatCom paper, we actually added phospholipids or lecithin that, believe it or not, is not only the fat, the minor components that are in there, like phospholipids, free fatty acids, and what else, other mess, affect the crystallization and polymorphism. And we found out that certain phospholipids form reverse micelles in the melt, and then they associate with the crystal, and we could actually get to a stable polymorphic form without tempering. So we didn't have to do the whole tempering regime. We just do something very simple, cooling and heating, and we can get to the correct crystal form. And we detected, if you understand these things from all the talks we talked about, we detected a very strong guinea, and the guinea was associated in the melt with the formation of a self-assembled structure of phospholipids. And recently we, it's really interesting. So remember I told you the 3L64, this is the 002. For properly tempered chocolate, if we actually take DMPC, the phospholipid above its critical aggregation concentration, so when it's a ball, right? When it's aggregated, we temper the chocolate properly, and look, none of the 2L here. But if we are below the critical aggregation concentration in blue, we actually see quite a bit of the 2L present in there. So somehow this phospholipid is doing the job in there. And what Jarvis did in the end is suggest that you have the incorporation of the phospholipid. Look at these lamella, right? That's a bit of a exaggeration maybe, but it makes a good diagram. And as it gets crystallized and squeezed within it, the hypothesis we put forward is you create a slip plane between lamella, which allows the tilting of those chains in order to form the correct polymorphic form. So you start at certain temperatures with the existence of these, and then they get smooshed to death, and the material goes straight into the beta form. So that's the idea, is you create slip planes that allow mobility of the chains in chocolate. The only problem is we got also with that system microcracks. We're trying to solve this problem. We want the correct polymorphic form, but we find cracks. That green stuff is little cracks. And this is 200 microns here, so you can imagine you have little cracks in the chocolate, which then propagate to a visual appearance of whiteness and a weakening of the material sometimes. And this is a computed micro CT. And this is a piece of chocolate. The green is the fat, and all those particles are the sugar and the cocoa powder. And you can do size distribution of the particles and stuff like that, and study the density of the fat when it crystallizes, and then talk about tempering. Yes, sir? It's purely density differences. Purely density. Another excellent question. Many people have proposed that blooming is if you get cracks and you get some liquid oil, it travels up to the surface and creates a surface of crystals. Imagine if you had a smooth surface and now you have crystals standing up like that, light impinges and it scatters light, and that's your bloom chocolate, usually an uncontrolled crystallization to form 6. You could say that some people would not be very happy to have cracks because that could induce bloom formation. You start heating and cooling. You're in a store here in Cargèse and put your chocolate next to the window. It heats you in the day. Then at night it cools down. Heat, you start peristalting, pumping the oil outside. And if there's a crack, it finds its way to the surface and you get uncontrolled crystallization. Yeah, that's not very good news. Chocolate maker would not be happy. Yes, sir? I've never heard that one, but that is absolutely possible because you're also in that form 5, and you got one more form to go, and bloom is usually associated with form 6. Maybe the cracking gives you a little extra, any extra energy, if it's thermal or even mechanical, would definitely enhance the transformation, but that has never been actually mentioned before, so thank you. So polymorphism, nucleation, mamma mia. So very quickly, we need to understand nucleation. So you're working with fats, you would like to characterize nucleation. I think nucleation is like the end-all of end-all. So here you have something that the alpha polymorph, which has a very high rate of nucleation. And here you have the beta polymorph, or beta prime in this case of milk fat, depending on the undercooling or supersaturation. That's how you get this. And look how different the microstructure is depending on the way that you nucleated it. So when you do a crystallization, please, 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 there's many ways of doing the experiment. Isothermal, I don't know what I'm doing, and non-isothermal, okay? So most work is here. Yeah, because everybody has poor temperature control. Isothermal means infinite cooling rate, right? So you're going from temperature, let's say molten, like 40 degrees to 10 degrees in 0 seconds, so that you can use the formalisms and talk about a delta T. Now, what the hell is a delta T here if your temperature is dropping in time and somehow your crystals start appearing? Good luck to you on that one. Stay away from this. Know how fast you can cool your system. Don't try to cool a bucket of fat, okay? Make it small or something like that. And the non-isothermal, that's a different story. This is also very relevant, but now you have a controlled cooling rate, an appearance of crystals, and remember that everything's governed by the supersaturation. How much below the melting point are you? And this is how much below are you in time? Well, here's like you're just below. Here's like no idea. So different ways of approaching it. I would suggest stay to the top, unless you're very brave. Yes? 20 degrees per minute. That was just a theoretical. Actually, it may not have been. This minutes. I'm sorry, I should have put minutes. Yeah, usually you're talking about minutes, and I'll show you the machine that I like in order to do it. Probably that's what you were getting at. You can do it with a DSC, but the sensitivity is not as high. You have to rely on some sort of light scattering. It doesn't have to be fancy scattering. It could be like a little laser impinging on it. That's to look at the turbidity. You try to detect the initial turbidity, and the better you are at detecting initial turbidity, the better it is. Petroleum industry has a good machine because they're interested. You cannot have the fuel crystallizing. So the petroleum industry has developed an instrument. So this is the driving force for everything, sort of. I'll tell you about it more. Is how much below the melting point of the fat you are. And I put set here and not crystallization because people confuse the temperature you set the machine at with the temperature at which things start crystallizing. You could use both, but you just got to know what you're talking about. So set means like I pressed a button. Gareth went, go to 5 degrees. Yeah. Oh, it's exact. It's 32.6. So good luck to you in finding the melting point. Don't come asking for your money back for me. I don't know. I don't know. Whatever works. I mean, it's really, I don't know. Yeah, it's a conceptual melting point. But why are we interested in the delta T? Just very practical. The delta T defines the chemical potential. And the chemical potential is really like the fancy way of saying, delta T, how much below you are. And the chemical potential, changing free energy is a function of the number of moles it's a partial derivative at fixed temperature, pressure, and total amount of components that are in there. You can read more about it. If you haven't done solution thermodynamics, it's like a nightmare to try to understand it in 2 minutes. But there's something you can do, which is, for example, the difference in chemical potential between the solid and the liquid, that driving force, right? Sugar solution, hot, everything is in solution. You cool it down, it starts crystallizing. You got a driving force, right? We're talking about that driving force. That's related to the supersaturation, where supersaturation is, at what concentration are you? What's your maximum concentration you can take? Your supersaturation, it's how far above of it are you, is the driving force. So even just looking at that, you can calculate it very easily. You have a temperature and the universal gas constant, you can get that in a solution. Now, in a melteur, it's different, even though they're the same thing. So you have the enthalpy of melting that you determine from a DSC, the temperature of melting, and our famous delta T. And of course, you can combine one with the other one. From this is very easy for us to get because everybody in fat industry has a colorimeter, and with that you can get these two parameters. Yes, sir? No? Sorry? Yeah, it's highly enthalpic, even though one may argue that there's an... Correct, but that the driving force is more than just enthalpic is what you're saying. Yeah, well, that makes sense. But this is the supersaturation that most solution chemists talk about. So the DSC I told you about, I don't know if you're familiar with the machine. Very quickly, your sample, a reference. There's more fancy ways of doing it, but this is an oven. So you heat up the oven, and you measure the difference in temperature between one pan and the other one. Up. We go, oh, phase transition, latent heat. The reference sample still goes up. The other one stays behind. That heat is going to the phase transition. And the delta T is related to a heat flow, MC delta T. You have to know the conductivities of everything, but that's how most of these instruments, if not all the cheaper instruments, work like this. That's called a differential temperature machine as opposed to a temperature compensation machine. A microcalorimeter is a temperature compensation machine. More fancy ones are, but the ones that are dominating the market are these differential temperature machines. And you get, you put your 10 milligrams inside there. That's the benefit of these things. You can work with really small samples. You put them in aluminum. Each one of those things costs like $2. Each one of those pans. It's ridiculous. And then you get patterns like this. So here we go from hot to cold, and we get an enthalpy of crystallization, which is the area under the curve. The temperature of crystallization here is shown as the peak, but most self-respecting chemists maybe talk about the onset. I put both and let everybody scream at each other alone. I'm too busy. And then here's the melting part. And then you can get the enthalpy of melting and the temperature of melting, the two parameters that we needed in order to calculate the chemical potential. So at least conceptually, you're addressed one aspect of the crystallization process. And then you can come up with tables like this. And for example, this is something that has a really high melting point, 20, 30, 40, 50, 60% of that in a liquid oil. And you measure your enthalpy, which goes up. Obviously, because you have more solids, you have your temperature of melting, and then you can very easily calculate your chemical potential difference, and you can also put a number for the supersaturation. The problem, at least this is an advance relative to before, people would go, oh, look, milk fat looks different from fully hydrogenated canola oil. Wow. It's like, yeah, one has a melting point of like 60 degrees, and the other one has a melting point of 30. It's like, I mean, if you put it all in terms of what supersaturation they're experiencing, you probably find out that they behave very similar. Nucleation, at least the way it's understood, classic view, you actually form, so you have a melt, you form a ball, it's supposed to be spherical, which again, actually I'll show you evidence that the ball thing is not too wrong. I'll show you more about this. And then what happens when you form a ball of these spiders, triglycerides, you form a surface interface between the solid and the liquid with a minimal interfacial tension, but a measurable interfacial tension. I always found that really weird, that a liquid and a solid triglyceride would actually have an interfacial tension in between them. Whatever. So you create a surface with an interfacial tension. This is a cool area to get into. It's sort of a little, and this is just the area of a spherical nucleus, you know? And then you have the volume element. So this is a positive contributor to the free energy. It's like no good, right? You don't like interfaces. And this is the good part of the free energy where you actually want to decrease the chemical potential. And that's a volume term, and that's just the volume of the nucleus. And here is your delta U's, and this is just the density of the material. So cool. If you mess with that equation a little bit, put some numbers that are unrealistic and stuff, and then you get a maximum, and as a function of the radius of that particular structure. And what you find is that as you have bigger and bigger and bigger ones, you're creating more and more surface area, but at one point, the chemical potential term takes over, right? It's one minus the other one, and then you have this massive decrease, and now you have spontaneous nucleation of the material. Before here, the idea is that it's like, whoop, no, 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 whoop, no, no, no. And these things are not forming a big enough nucleus in order to go to the crystallization. So this is the story that you're told there, and this is called the critical radius, in which that's the minimum size you need in order for this magic to work. Now, all I did here is just put the, area of a sphere, volume of a sphere. The equation's the same. You differentiate equal to 0, maximum, minimum point of inflection. Remember that? And then you solve for RC. Then you put it back in there, and you shove it into here, and it gets really like funky. And at the end of it, you end up with an expression that looks like this. It's just arithmetic, and you end up that your free energy now has a whole bunch of these terms in here, which involve the interfacial tension, the density, the temperature of melting that Adam's going to give us, the enthalpy of melting, and the delta T for crystallization in the class. So all of them numbers that you can get. And so we understand nucleation from the Fischer-Turnbull model, in which our rate of nucleation is your NKT over H. But look at this exponential term here. And the classic view is that you have a free energy of nucleation, of crystallization, and a one of diffusion. And most people, that's another one, I'm going to be like yelled at, is like the free energy of diffusion is assumed to be 0. Because it's too hard to get. And so you're like, get it? And so now you have, remember we had a term before? And then you shove it in there. And look at this. This is what they do here. I'm going to get yelled again. I'm used to it. That the rate of nucleation is inversely proportional to the induction time of crystallization. You can do it in another way. We've done it by microscopy, but this is what Gareth was talking about. How do you determine this ambiguity? This is called a petroleum analyzer. And the petroleum analyzer is really cool. There's a very well temperature controlled, a really, really good temperature control, and you put 150 microliters always with a positive displacement pipette in here, and it controls the temperature like crazy, and there's some massive scattering that goes from above. You just detect the cloud. It's a cloud point analyzer. That's the best you can do, really, unless you build something else. And you get something that looks like this. And so there's a certain dead time, right? And then an induction time, and then your turbidity starts going up. And it's really early, and way earlier than anything you detect by NMR, way earlier than anything you detect by DSC, like a lot. Like, well, this was very warm that we were doing this, but I would say compared to DSC, which is quite insensitive, it's at least half of the time. So by the time you get a DSC signal, by the time you get a solid fat content signal, like it happened. So you can build one with a laser yourself. You don't have to like buy that thing. And so what do you do with that induction time of nucleation, right? So it's up to you. I'm not going to get into this, whether you throw a line here and call that induction nucleation, or you say it's departure from the baseline. I'm like too old to do this, like the discussions. You can report both so that people cannot yell at you too much. Then this is the Fischer-Turnbull plot, classic Fischer-Turnbull plot. All I did is take that equation, remember the equation? That long one that looks like a nightmare? And the plot you have to do is, if you rearrange it, is your induction time times the temperature that you set it at. And on the other side, you have the temperature and the delta T that you use. All you need is temperatures. And so if you do that plot, notice here, natural log of tau T versus 1 over T delta T squared, you get a straight line, if you're lucky. And you get the slope, and that slope is called M. And M is all of this nightmare. And now, if you believe me, all you need to do is M times Boltzmann constant divided by delta T squared, and you have the free energy nucleation. Very, very you can look at it and go, oh yeah, whatever, grade 10 arithmetic. And then you have also the slope term, which again looks scary, but it has just a density, a temperature of melting, an enthalpy of melting, and Boltzmann constant. Totally, totally usable. And then you can get, this is one way of getting to that interfacial tension term by kinetic analysis. So you just do the cube root because it's in there, and you have the slope you determined for the Fischer-Turnbull plot, you have the enthalpy of melting from DSC, you have the density because you read it, and the temperature of fusion, and you can get that. We sort of believe it. But we've used it as an indicator. But it's not 100%, but you go out there and try to determine the interfacial tension differently. It's not that difficult. And here's just the conversion between density and that molar volume for you to use. And because I was very lazy, I didn't calculate the free energy of nucleation. But here are the induction times. And look how much, if you crystallize cocoa butter at different temperatures, you can see how the induction time of nucleation is really related to the alpha polymorph, a mixture of the two, the beta prime polymorph and the beta polymorph. Yes, sir. 10 millijoules per meter squared. I've had 5. 10 is a good number. Non-isothermal kinetics, different. We developed the formalism. I leave the reference here for you. It's probabilistic, so it's not very complicated. As long as you know a probability density function is like pretty cheesy, but it works really well. Yes, sir. Absolutely. That is very sensitive to, I mean, you would have a much lower free energy nucleation for an alpha form if you did that plot. Oh, it's just structural. It's just structural. Because what happens is like the molecule, the viscosity of the melt increases to such a point they cannot diffuse anymore. And there seems to be a time constant related to the alignment of these long, long chains. There's 3 of them. There's a glycerol core. It seems to be like computationally difficult. So there's a definite time constant that it's almost like the supersaturation is calling you to crystallize, but this rearrangement that needs to take place in order to form the crystal is very expensive in terms of time. That would be reflected in the induction time. Yeah. Absolutely. That's part of the thing that is missing in there because, well, the diffusion gets screwed up for everybody. Then this year we finally recovered a work on, so what's the structure of the liquid state? This came out in physical fluids. They love food science now, eh? They love us. So like kitchen flows and, you know, they forgive all kinds of mistakes we make. So what we did is we grabbed a triglyceride molecule and look, we put deuterium right around the glycerol core. Because we had the impression that, okay, so how do you visualize this nucleus from being formed? I'm not going to tell you about the history of this. Please read the paper. It's a history of yelling at each other, of what the structure of the liquid triglycerides are. Do they form waves, lamella, little lamella floating? Imagine that idea. Little lamella floating, liquid lamella. Ooh. Liquid lamella floating in the fluid and pneumatic. No, it's smectic. No, you... Larson yelled at poor Cebula, who was a young guy, told him he was an idiot because he said there was a pneumatic phase, and then they kept on, and then there was just 30 years of yelling at each other. So at the end, we didn't solve the problem. Michael Rapolt from Leeds really finally did the more definitive study on this, and it was great work, and this took too long. So we put deuterium. This is a nice thing about neutrons, right? You can put deuterium where you want and see what's happening. So look at this. We actually found this very broad scattering from the liquid. Liquid triglycerides scatter in the liquid state. They form structure, they form clusters. It's big, actually, the scattering. It's here, and in X-ray it looks even bigger, I didn't show you. And then we put the deuterium, and look, because of scattering length density effects, right? You know, so you get a massive increase in the scattering when we put the deuterium in there. So hence, again, that particular structure was related to the glycerols that were hanging out together. You see they're there. And then I'll show you, look at those. Those are some simulations we did. You did. Giuseppe Milano from Italy is our collaborator. And the story about this is that we had modeled the crystallization of PPP, palmitic. There'll be a test on the nomenclature at the end of this. You have to know what lauric, myristic, palmitic, behenic is. No IUPAC. No. It's all like the funky names. And we had actually looked at the crystallization and the formation of lamella. So he did some coarse graining. This is how he coarse grained it. Not going to get into the details, don't have time, and probably cannot explain it to you very well either. And, you know, the lamella form, really, really cool. So we told him, hey, we have some neutron scattering studies. Could you look at the early stages of your simulation to see if there's anything there? And we're like, no. He found it. He found these clusters being formed. And in the paper, we actually have the size of those clusters. They're the same ones we estimated by estimating some like close filling. What is it? A C22 is a close filling geometric feature there. And they came out pretty close. So he did the analysis of this, and it came out as a structure that corresponds very well to this feature here and to our calculation. So those clusters were stabilized by glycerol, and they were roundish things. So that brings up the question, can you do something in the liquid to affect the solid? We have some evidence that we can do that. We can make cocoa butter stir before the melting point and above in the liquid, and you can affect what happens in the solid state. So that's a little funky. So it is possible, like in Kevlar, right? So we did nucleation. Now let's do crystal growth. We used the Avrami model, classic metals, and you have this, that's a sigmoidal. And it's not a bad model. It's actually based on theory at least, and not somebody's like current purchase of a curve-fitting software, which happens a lot, It's like the thing they have invented, like they have discovered the moon when you do a Gompertz equation. At least this is based on some theory. See, we have the solid fat content we can measure, and there's a rate constant and a coefficient n. The coefficient n is the dimensionality of growth, and k is sort of some weird unit rate constant of crystallization. And the nice thing is that you can maybe imagine that if you have a coefficient of 1, it is a needle-like from instantaneous nuclei. They appear like this. Sporadic is like in time. So this changes if you have a one-dimensional structure, some two-dimensional surface, or some ball. One-dimensional, two-dimensional, three-dimensional, and it's affected by the nucleation. Instantaneous, sporadic. And you can look at it, right? If you have different sizes, it was sporadic, right? If all the crystals are the same sizes, probably was instantaneous. And then, of course, this never happens. You get 2.3 or something like that. And then there's papers and people justifying why it's 2.3 and not 2, But I don't care. I have my index of crystallization. And so it fits the data fairly well. And so you have, this is just the SFC measurement, and you can derive from this an N and a K. That gives you at least a measure of crystallization speed. Very different. If that's analyzed and has an N equals 1, N equals 4, at least you can look at it and say maybe that's how it was. If you don't want to do curve fitting in the nonlinear regime, you can linearize this thing with a double log plot. And warning, it just looked like this, which doesn't look very linear to me. But if you take this region here, you come with a number that is pretty much the same as the other one. So whatever. You can do it in Excel. Excel does nonlinear now, so it doesn't really matter. And you can get, so this is another way people do it. FYI. I proposed at one point that we could have multiple crystallization events, so it's just a summation of Avramis. And it actually does work quite well if you have something like this, for example, and you can get one species, two species, present, each one with an N1, N2, K1, K2, and you can characterize that as well, as opposed to, it doesn't look too bad, right? You can put this through and people would believe you that that's good, right? Like no problemo. But I mean, in reality, you have two species that something comes up maybe and something nucleates on that, so the story changes a little bit if you adopt multiple species. And that's, again, showing you how cocoa butter crystallizes isothermally at different temperatures. The Avrami exponent, how it changes for a more that's actually pretty close, eh? Three-dimensional, and we all know that these are pretty needle-like. And look, that's around 1. Don't get too hung up on the fact that it's 0.8 versus 1.1, right? So it's around 1, and the other one is more like a three-dimensional growth. And when you look under the microscope, you actually see domains that are gigantic, like 100 microns, and they're balls. They're not balls, but be very careful when people look under the microscope and try to say something about the polymorphism, because these were all crystallized in a certain way that would enhance the formation of the alpha form. I haven't given you the conditions there. Now, all of these have a different temperature history for the beta prime form. So all of these, if you put in the X-ray diffraction unit, you get the 3.8, 4.2, you say it's beta prime. You don't know what that means, but you say it's beta prime. But look at the microstructure difference between all of these. All of them are beta prime. So it depends on how you got to the beta prime. That's sometimes, did you cool it, heat it, beat it up, kick it? What did you do to it? Cool it down again, and you get a different microstructure. And look at this. You can actually have a very fine-grained triclinic if you cool it and stabilize it, as opposed to you let it do whatever, you get sunflowers. You know, you can get all of this. So this was actually a good point to make, is like, don't trust what you see under the polarized light microscope and call it something. So microstructure very quickly. What I came to the field and people tell me, oh, look, there's a crystal in there. Like this looks like the summer here. What about that? That's a crystal? Don't tell me, oh yeah, that may be a crystal. Is that a crystal? That's a crystal. That's all in polarized light. I'm like, what is a crystal? I asked that question for more than 10 years. And then I found 3 papers in the literature, one of them by Ewell and Miara, these Eurotypes, right? 70s, Pureral 75, and Herce and Lunis. I hate Herce, he did it all before me. So I mean, there's nothing I could do, I'd always find he did it before. And so on one side you have the guy showing you the sunflowers, and the other side you got guys showing you this. And it's like, yeah, they're schizophrenic. And so these are one of these really nice TEM, SEM techniques when you actually do replicas, you know, carbon replicas of things. And you see something that a chemist would identify as maybe a crystal, right? Regular size, sort of looks like a crystal. Then we did some AFM on chocolate, on cocoa butter, and we found something that looked like platelets. Then we found clouds, and then we had like the whole sky. And it's like, well, there seems to be a hierarchy of structures in there. And maybe those guys were looking at the bottom of it. What else were we doing? We started learning to use carefully the width of the peaks in an X-ray diffraction, as low Q as possible, to not have instrumental broadening, and et cetera, et cetera. And what do we do with a full width half maximum? You can derive a share. You use a share model to derive a domain size. So you saw all those crystals, and domain sizes are like 20 nanometers. It's like, what? Like 20 nanometers, 100 micron crystals on the microscope? What the hell's happening? And remember, this is the 001 reflection, so you're looking in the direction of 001. So you're looking at the lamella, right? How many lamellas are there in a domain? That's what that means. That's what we discovered. And we found that it was correlated. I mean, who gives a hoot? You know, it's like, it was related to all kinds of things. Water vapor permeability, when you have a fat film and you want to prevent water from going through, highly related to the domain size. What about oil migration through chocolate? There's a permeability coefficient related to the domain size in angstroms. And what about an apparent diffusion coefficient of the oil in the chocolate? Also seems to be related to this domain size. So the question is, what the hell is the domain size? I mean, seriously, before 2010, nobody could tell you that. Then came, I told Nuria, you're a postdoc. You don't have anything to do for the next 4 years. I need to go on holiday. And so you extract nanoplatelets or crystals, and I'll talk to you sometime later. And so cold isobutanol, break it up, sonicate it, filter it, sonicate it again, run to the cryo-TM. And this is Nuria. She's a prof at Iowa State. And voila. We isolated the nanoplatelets. We started calling them crystalline nanoplatelets. Okay, so some edging, right? The solvent erase, dissolve some of the edges. Yeah, forgive me. And you have to be careful not to melt the whole thing in cold isobutanol. And then I'm like, wow, that's great, let's publish. She's like, hey, Alex, have you seen things like this? I'm like, what the hell is that? That's snot. That's nothing. And it's like, no. Let's look at that a little bit more carefully. I mean, this is like on the money. You know, thank you, Nuria. These are actually individual lamella. These are freaking individual lamella. So it's like, now we know what a domain is. We can measure with a ruler and say, that's a domain, and this is the stacking of the lamella in the 001 direction at the base of the hierarchy of structures in fat. And now we take an X-ray diffraction unit. This is a lecture. So this is, all of a sudden we see 45 angstroms, and 45 angstroms, 4.5 angstroms. So 4.23 plus error when we do it with a ruler. So we know that we did X-ray diffraction by microscopy. Because you know, I know, we all know, that an X-ray diffraction pattern is a radially average Fourier transform of the correlation function. So whatever this correlation is in direct space, you'll see it as a reflection in reciprocal space. So it's like, wow, like it's all there. That photo is good. Then, of course, because we all are geeks and nerds, so you can go and have, you see in the background, the little lamella. You can get many of them like that. And then you go to Photoshop and you press on the fast Fourier transform button, and then it gives you the spatial periodicities. And look, 4.53 nanometers. It's like, make a t-shirt out of this, you know. And of course, I made a whole bunch of pictures for you, more. This is the artistic part. And this is very important in your career. You must have a diagram like this somehow that people can relate to. So we propose, again, updated in 2010, was lamella, nanocrystals, domains, little wiggly things, nanocrystals. Where are they? There they are, the nanocrystal with a length and a width and a thickness. Then we need to get to the aggregate, right? And then the aggregate forms a network, and the network forms a fat. I have you there. John van Duinhoven from Unilever has taken this further, and he now uses spin diffusion and MR. And he manages to get also domain sizes from that, and he's doing funky things like, if you have a wider distribution of domain sizes, you have a more plastic material. It gets really interesting, more plasticity related to your heterogeneity in the distribution of nanoplate sizes, thicknesses. That's why I don't get too excited. So these things are super sensitive to external fields. If you have a higher supersaturation, like 100%, or you dilute it with oil, you see gigantic changes in the size of these things, just for you to see. If you have a greater supersaturation, you can change things from almost 400 nanometers to like 200, like it changes a lot. And so does the width. If you, forget the thickness. If you actually, slow cooling, fast cooling, look at those huge changes in the length and the width. You don't affect the thickness too much. I'm still trying to do that. And shear, you shear it, you can change size dramatically at the nanoscale. So maybe you have a structural target for your functionality, you have a nanoscale picture. You can do it with cooling rate, or you can do it with shear rate. Actually, not too much. It's we're talking 5 to 8 degrees per minute. That's all. As opposed, shear rate. Sorry, with shear rate we're using 100 seconds to the -1, 200 seconds to the -1. That doesn't affect the orientation, but it does affect the. In order to get orientation, you have to put the Peclet number and know exactly how much above you are at the shear rate over the rotational diffusivity. That gives you like an impression of that. Look at that chocolate. When you crystallize chocolate, you extract, you have these gigantic needles in the micron range. You start putting it in a shear field or a laminar shear field, and you immediately go from microns to nanometers in the length. Let's just focus on the length. So you change the aspect ratio when you temper chocolate. And you can affect things like, obviously, things like effective diffusion coefficients of oil, if you got static, sheared, oriented. Same amount of solids, very different crystal sizes. That's sort of like really equivalent sphere of a nanoplatelet, so forgive me. The equivalent sphere of a nanoplatelet, but look at those gigantic changes. And here you have a, you look at the ratio of the diffusivity of a molecule in the oil versus the diffusivity when you have a fat crystal network, and you can have like 4 times greater when you have the network in there. And what else? And this is Darcy's law permeability coefficient. The lower permeability, medium permeability, and the higher permeability as you go from static to sheared. So sheared is good to prevent like oil migration. We also managed to work a little bit with surface nucleation on the surfaces that I talked to you about, and we can actually change the thickness of the platelets from 5, 6, and 7 lamella based on shear. But this shear is shear. In a scraped surface heat exchanger, at infinite cooling rates, the ammonia valve was open, and it was as fast as the machine could go. And we're talking about a blade, soft blade, ripping a surface that is at minus 20 degrees, and you're going at, I think we were having this gigantic machine at going about 300 RPMs. I don't even know what the shear is in there. It's like absurd on an extremely thin layer. And with that, we could change the thickness of it. So it requires like a lot of shear. Yes, sir. Here, absolutely, it's all nucleation driven. If you want to make the perfect plastic fat, you destroy the mesoscale. It's all a nanostructured material. The moment you have these domains like this, you start introducing brittleness in the material. And so we could make a laminating fat that was so good that this is the control commercial, and this is what we managed to do. That's a vol volant. I learned that that's vol volant without the shrimp filling. You know, so you get massive expansion when you bake these things. The fat immobilizes layers of dough, so when it cooks and you have steam coming out, they cannot go from one layer to layer, so it opens up like an accordion. That's when you make a croissant or something of good quality. A bad fat lets those things bind, and not as good. So the clusters, I think we can do it. So when we're looking at those things, we're looking at the microscope and we look at micron-sized things, unit microcrystal, and believe it or not, when you increase the supersaturation, like I showed you before, we get a reduction in crystal size because that's what should happen with nucleation. Increase the supersaturation, goes faster, and you get smaller crystal for the same amount of solids. But we take the picture under the polarized light microscope, and this thing is going the other way. It's like, what the hell? This is governed by the laws of chemistry. This is like drunk. It's going like the other way. How come I get bigger microcrystals when I'm getting smaller nanocrystals? And so we went in the literature, and of course, it had to be Hertz again. And you know, he had these pictures of these things, and he calls them crystal clusters. And we're like, damn, there must be crystal clusters. So why don't we make color pictures out of it and do Monte Carlo simulations with David Pink out of St. Francis Xavier. So in the end, we managed to create a nanoplatelet, and I'll show you how. And maybe these things aggregate via the 001 planes and form these linear structures, which then can aggregate and form mass fractally things, and then the whole thing keeps on aggregating until who knows what. David is so funny. I mean, those of you who are older here, you know what he called these? He called it tagwoods. Anybody remember Dagwoods? Dagwood? Dagwood was this comic thing, it must be in the 50s, of this guy who ate these gigantic sandwiches. He would stack it. You maybe have seen it in 50s comics, very retro. And he had this gigantic sandwich with ham and cheese and they're about this big. So instead of, and his name was Dagwood. So he called these tag, as in triglyceride, wood. And the funniest thing is that it's a joke that we put out there, you know, because we invented this stuff, right? So it's like, then we go to these conferences and like these serious people, and you can see the formation of the tagwoods. It's like, they're talking about a sandwich. So we did a lot of work in the USACs in Argonne. We spent so much time there. You know about scattering. That's a characteristic length scale, 2 pi over q. I told you about polymorphism and the small angle region. USACs is like where no man or woman has gone before, like over there in really small. And you get patterns like this. Now this is scattering as opposed to diffraction, and you have to make some idea of what the hell that is. And people use it in your field because you can study big things in the micron range there. This is the kind of thing we got for fats, and we got a Poirot region where you have a smooth surface, Poirot slope of when you have a sharp scattering length density interfaces. So it's smooth, just smooth. So you're looking at molecules with molecules, the surface of this thing. Then we have a change in slope. That change in slope is the radius of gyration of whatever was smooth, and that corresponded very much to the size of the nanoplatelet. And then we kept on going, and guess what? This slope was a mass fractal. And then we got a second RG2, which was 1 to 2 microns, with what you see under the microscope. And we're like, beer time. You know, and then up here, this P3, we had no idea what it was. It can be surface, it can be mass, depending on whatever it wants to do. So you can imagine, right? Cluster aggregation. You can talk about all kinds of things. And if you need to know, I put it here. We analyzed it with the Bocage model, and the Bocage is a marriage between Guinea and Poirot by Hamouda. Hamouda implemented it, but of course this is Bocage's model. It's called a unified fit. Good luck with that. it's you decide how many levels there are, and you solve for some nightmare of error functions to exponents and to like, you can imagine. But it works. It works really well, and you can get this implemented in Irene and stuff. This is David Pink. He's getting really old, but he's still super active. He wants to work. A man looking for a job. If you need a theoretical physicist, 2 things you got to give him: red wine and coffee, and talk to them. Because, I mean, nobody talks to them. But if you do those 3 things, they'll be your friend forever. So what he did is he created, spheres interacting via van der Waals forces. Then the interactions are all the same, by the way. And then he did just Monte Carlo simulations. And he obtained different microstructures. And what did he do? He just calculated the structure factors from those things, but the relative position of each little ball that makes a the platelets relative to each little ball. It's a big summation. And then he predicted certain slopes. Almost there. The story comes here. So this is the end of the story of USACs. And here we have the scattering pattern. We have a lot of data behind this, but his simulation is, at the beginning you have the primary unit is a surface fractal, Poirot usually. Then you have a mass fractal, the aggregates, which are the aggregates of the primary units. Then you have something that could be like a surface or mass fractals, and these things can be smooth, they can be rough, they can be diffuse, depending on the value of that slope. And he interpreted that as covered with oil or not covered with oil. You can have, in the mass fractal, can be very linear. If you have tag woods, they can be diffuse as well. They can form like clusters of snakes. And here you have surface fractals or mass fractals. And the RG as a size gives you the size of the nanocrystal. The effect, assume it's an RG. And that's the size of the microcrystal. Makes for good papers. John van Winhoven has taken this further. He does Raman confocal, and he can image these clusters now in 3D and get fractal dimensions, flock distributions, flock porosity, and he uses this weak link theory of that. So this is the 2020 version of the same thing we put together in the mid-90s, but in color. We finally got to the color picture. The information hasn't really changed in there, but it is color, and it's in the correct aspect ratio to be modern. New things that people from Belgium are doing, they're using the USACs in order to look at the dynamics of crystallization. It's exciting. In Grenoble, they get a spectrum like in sub-second now. And they use now a geometry. That was a model independent, is called model, so you don't know what geometry you have. They actually introduced the actual form factor of a platelet. And they can see how one grows, the width and blah, 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 and the thickness and the whole thing. It's super exciting. You see basically the assembling of this platelet in real time. I gave you the reference there for that. And what else did he do? And he also sheared it. And that's probably something you guys are interested in. I mean, he has, this is the way that in food science they do thixotropy, by the way. You have a viscosity, then you shear it, and then you wait a little bit and you measure how it recovers in a run. And they actually took USAC's images of how these things are arranged at each one of those shear rates. And the references are there. And it's really, really nice. And you can read what follows is we just have a... just wanted to show you. This is finally what we consider to be a fat crystal network. This will take one minute. Clusters made of particles. The particles are the nanoplatelets. Of course, they're spherical here. And they interact very weak link. I just wanted to make sure that you understand we're not in the classic strong link regime. We assume that these are hard and this is soft. That's the only way I can see how a ball transduces mechanical energy to the next ball. I cannot see how a string of cotton balls can transduce anything, but that's my fault. So these things are hard, and so when you go good is what it's in between. Makes it simpler too, even though not correct. And then we can look at the growth of the crystal and the formation of these clusters in time. And we eventually did that. The whole thing is I'm just going to get to the point. That is, as you will see, I'm going to get to the final formula. Is we managed to develop the formalism not only to describe, according to the weak link regime, the exponent of the volume fraction term. That's the amount of solids, like 10% SFC. And here we also derive for the pre-exponential term. And the way I simplify the van der Waals things to the point where I use a semi-classical approach, and that's your interfacial tension. And that's the size of a platelet, and that's a critical strain when you just are pulling things apart and like forces no more. And I don't like that term. And this is very classic one-dimensional compression, by the way. And then what I did is I just multiplied the critical strain by the modulus before, and you place the expression in terms of just the yield stress, if you can measure that. And the yield stress is very simply related to the volume term, to a fractal dimension. The interaction between particles related to an interfacial tension term is an indicator of strength of interactions, and the size of your primary structural unit. Doesn't get easier than that. And it works really well. You can model a lot of systems, and this was the beginning of us trying to understand, this happened before the other one, why you get a size of 130 nanometers when I'm looking under the microscope and I see something that is 2 microns. And that took us there. And with that, I leave you, I thank you for your attention.